In the last video, we saw how the circulation depended on the vector field. So we had the same curve, but two different vector fields. But in this example, we want to see how the circulation changes for the same vector field, but different curves, or in this case, line segments. Okay, so first one, we're going to look at the line segment C from 0, 0 to 1, 1, which is this pink one right here. So this is A right there. All right, so let's look at A. For A, we want to parameterize that section of it. R of t would be t, comma, that's a line segment of slope 1. So t, comma, t. For 0 is less than or equal to t, which is less than or equal to 1. The derivative of that would be 1, 1. And then the vector field is complicated. So the vector field is equal to, okay, so now remember, this is now our x, and this is now our y for this particular piece. So you take t, comma t, you divide it by the square root of t squared plus t squared, which is t, comma t over, that's 2t squared, right? This right here is 2t squared. And then that would be t times the square root of 2. All right, so putting that together, t over t makes 1. So that's 1 over the square root of 2, 1 over the square root of 2. Okay, so let's put that together and let's find the circulation. The circulation would be the integral from 0 to 1 of 1 over the square root of 2, 1 over the square root of 2, dot product with 1 comma 1. Right, again, that had a slope of 1. Right? It's got a y-intercept of 0, slope of 1, so therefore, right, the ratio of those has to be 1 dt. All right, so then we just put that together, right, find that dot product. Sorry, I wasn't happy with my 2 there. So this is the integral from 0 to 1 of 1 over the square root of 2 plus 1 over the square root of 2. So 2 over the square root of 2 dt, which that's 2 over the square root of 2 t from 0 to 1, which would be 2 over the square root of 2, which is about 1.414. Let's put that right there. All right, so that's A. Now let's look at B. Now, which one's curve B? Curve B is from 0, 1 to 1, 1. So over 0 up 1 to 1, 1. So it's this piece right here, right? So this is B right there. All right, so let's do B over here. We need to come up with a new parameterization every time because all of our curves are different, unlike the last problem we did. All right, so for B, we want t, comma, it's 1, right? The y value is never changing, it's 1. All right, and we're going from 0 is less than or equal to t, which is less than or equal to 1. Our prime of t is 1, comma 0. And then the new vector field is t, comma 1, right? So x, comma y over the square root of t squared plus 1 squared. All right, well, I don't need to write that in a different way. We'll just leave it like that. It's fine. Okay, so then the circulation would be the integral from 0 to 1 of, we're going to take the, actually, let me write it still in the fraction form. It's just going to be so ugly to write it otherwise. So t, comma 1 over the square root of t squared plus 1, right, because 1 squared is 1, dot product with 1, comma 0 dt. All right, so 1 times t is t over this thing, and 0 will be 0, so we don't worry about that. So that's the integral from 0 to 1 of t over the square root of t squared plus 1 dt, which we can do with maple, and we'll get 0.414. And here so you can see it. There's A 1.414, and then here's B 0.414. I was not lying to you. That's really is it. All right, now let's do part C. Okay, for part C, let me go back to blue just so we can keep these straight. Okay, part C is the line segment from 1, -1 to 1, 0. You know what? I should put arrows. So this one was going this way. This one is going this way. This one's going from -1, 0, which is right here. Oh, no, C, sorry. 1, -1 to 1, 0. 1, -1 is down here to 1, 0, which is right here. So that's that direction. Okay, so let's think about parameterizing that. R of t would be 1 is fixed as our x because it's a vertical line, and then t. And we're going from -1, which is less than or equal to t, which is less than or equal to 0. R prime of t would be 0, 1. And then our vector field is x, y, so that's 1, t over the square root of 1 squared plus t squared. Right, again, so you couldn't do the normal thing of letting x be t here because this is a vertical line. So this has a fixed x value of 1. So it's 1 no matter what for the x, and so you let the t be your y. That's a different one than we usually are used to seeing. Okay, so let's put this together. The circulation is the integral from -1 to 0. And then we're going to take the vector field. Oh, sorry, I just want to put that in the numerator. So the vector field 1, t over the square root of 1 plus t squared, or t squared plus 1, right, times that by 0, 1 dt. And similar to the one above, right, the first component's going to drop away because it's times to 0. So we're taking the integral from -1 to 0 of t over the square root of t squared plus 1, which is going to be -0.414. Okay. And then lastly, let's look at D. So far, this vector field is helping a lot, helping some, not helping at all, right, in the negative direction. All right, let's look at D. D would be this component right here. Right, we're moving along this way from -1, 0 to 1, 0. So this is D right here. Oh, I should have labeled those. Sorry, this is C right here. And let me erase that and put D in the same color so it's easier. Right, so there's D. All right, so going back down here, we need the parameterization of that. X can be anything, so that's t, and then the y is fixed as 0. The r prime, oh, and then we're going from -1 is less than or equal to t, which is less than or equal to 1. And then the derivative would be 1, 0. Now the vector field's going to get into a little bit of diciness here because it depends. So it's x, y, which is t, 0, over the square root of t squared plus 0 squared. Now, this is going to be trickier than you think because we're used to just going, oh, well, that's just t. But it's really the absolute value of t. It's just that most of the time we've been dealing with positives and so we don't care. But this is not positive. You see, for this section, it's negative. And for this section, it's positive. So that means that we're going to have to branch our vector field off into two directions. We're going to have t0 over negative t, right? Because we learned in basic Calc 1, if nothing else, that right, the absolute value of t looks like this, right? From -1 to 1, right? So we're going to have to go, right, it's negative t over here and it's positive t over here. So we're going to take it from t0 over t for the 0 to 1 part. And then we're going to take t0, t comma 0 over negative t for the -1 to 0 part. We're going to have to branch that off. All right, some fancy algebra. Okay, so that means that our circulation is actually two separate integrals put together. We're going to take the integral from -1 to 0 of the vector field. Well, if you look at this, this is going to be -1, 0, right? That's going to be your vector field. And this one's going to be 1, 0, right? So the vector fields are not hard. So this is -1, 0, dot product with the r prime, which is 1, 0, dt, plus another integral from 0 to 1, and that's going to be 1, 0, dot product with 1, 0, dt. All right, well, luckily this is very easy to do, right? This is -1 to 0 of -1, and then this is 0 to 1 of 1. So this is going to become -1, well, negative t, if you will, from -1 to 0, and this is positive t from 0 to 1. So this is -1, and this is 1. And that means the entire circulation was 0. Interesting. Now it does make sense. So let's go back up and look at the curves for a second. Okay, so if we look at A, you can see that the arrows are pointing along with A, that curve, right? So this is going to have positive circulation for A, right? It's a positive number and it's big-ish, right? Because the arrows are pushing along that curve, right? So this one had a positive circulation. Now B has a positive circulation, but it's not as big, right? Because the arrows, it's kind of going in the direction of the arrows, but it's, right, it's not going against them, that's for certain, but it's not getting pushed along nearly as well as A was. A is going with those arrows. So it's positive but small, right? Whereas this is positive but big, relatively speaking. Now C is negative because you're trying to move up this curve. Oops, let me put a positive here for B. Right, so B is positive. All right, C is negative. Right, you can see it's negative because you're trying to move this way, but all the arrows are pushing against you. Right, so that made it negative. Now what about D? Well, okay, so if we look at D, half the time, this half, we're moving against the flow, right? You can see the flow going outward with the arrows, and we're going exactly against it. So it's negative over here, but then over here it's positive in the same amount that this was negative. And so they end up canceling each other out. The negatives and the positives cancel, and we end up with 0. Sorry, I have a stray pen mark. There we go, right? So this was because the positive and the negative cancel each other. So as we saw from these two examples, circulation can change based on what vector field you're looking at. You can have the same curve, but different vector fields will have different effects, different amounts of circulation. And in this case, we saw we had one vector field, and the circulation changes depending on which way you're trying to go, what your curve is, and what does it go with the flow, or does it go against the flow, or does it cancel each other out, right? It all depends on which way or what path you're trying to take through that vector field.